Hello there, and welcome. Tonight, we're going to explore one of the most perplexing mysteries in modern cosmology, a discovery so strange that it challenges our fundamental understanding of how the universe works. We're talking about dark flow, a phenomenon where massive clusters of galaxies appear to be streaming through space in the same direction, pulled by something we cannot see. Imagine standing in a river. You watch the water flow past you, moving in one direction, seemingly pulled by an invisible force downstream. Now imagine that instead of water, we're talking about galaxy clusters, each containing hundreds or thousands of galaxies, all drifting together across the cosmic landscape. What could be powerful enough to move such enormous structures? And more importantly, where are they going? This is the puzzle of dark flow, and it's kept astronomers awake at night since its discovery. But before we begin, please take a moment to like and subscribe, but only if you enjoy what I'm doing here. Also, leave in the comments where you're tuning in from and what time it is there. It's great to see how these videos connect people from around the world. Now get comfortable, dim the lights, close your eyes if you'd like, let the city noise fade away, and let's begin. Let's begin with a basic question. Is the universe moving? The answer is yes, but perhaps not in the way you might think. When we look out into space, we see galaxies in every direction. And here's the remarkable thing. Nearly all of them are moving away from us. This isn't because we're at the center of the universe, or because galaxies find us particularly repellent. Rather, it's because space itself is expanding. Think of it like this. Imagine you have a balloon with dots drawn all over its surface. Each dot represents a galaxy. Now, as you inflate the balloon, what happens? Every dot moves away from every other dot. If you were standing on any one of those dots, you'd see all the other dots moving away from you. That's essentially what's happening in our universe. This expansion was first discovered in the 1920s by Edwin Hubble, who observed that distant galaxies were redshifted. Their light was stretched to longer, redder wavelengths. This stretching occurs because the galaxies are moving away from us, much like how the pitch of an ambulance siren drops as it speeds away. The farther away a galaxy is, the faster it appears to be receding. This relationship, now called Hubble's law, became one of the cornerstones of modern cosmology. But here's where things get interesting. According to our best models of the universe, this expansion should be relatively uniform on large scales. Yes, galaxies have their own individual motions. They orbit within their clusters. They can collide with neighboring galaxies and gravity pulls them around. But when you zoom out far enough, when you look at the really big picture, these local motions should average out. The large-scale flow of the universe should be smooth and consistent, like a calm sea where individual waves don't disrupt the overall pattern. At least that's what we thought. To understand how we discovered dark flow, we need to talk about one of the most important tools in modern cosmology, the cosmic microwave background, or CMB. What exactly is the cosmic microwave background? Imagine the universe about 380,000 years after the Big Bang. Before this moment, the universe was so hot and dense that light couldn't travel freely. It would immediately collide with particles and get scattered. But as the universe expanded and cooled, it eventually reached a temperature where atoms could form. Suddenly, light could travel freely through space. That primordial light has been traveling through the universe ever since, and over billions of years, it has been stretched by the expansion of space into microwave wavelengths. Today, this ancient light surrounds us from all directions. It's essentially a baby picture of the universe, showing us what conditions were like when the cosmos was just a tiny fraction of its current age. And here's the remarkable thing. This light is almost perfectly uniform. No matter which direction you look, the temperature is the same to within a few parts in 100,000. This uniformity tells us that the early universe was remarkably smooth and homogeneous. But I said almost perfectly uniform, and that word is crucial. There are tiny variations in temperature across the sky. Some regions are slightly warmer, others slightly cooler. These minute differences are incredibly important because they represent the seeds of structure in the universe. The slightly denser regions eventually grew to become galaxy clusters, while the less dense regions became the vast voids between them. Scientists can study these temperature variations in exquisite detail using satellites like WMAP, the Wilkinson Microwave Anisotropy Probe, and Planck. These spacecraft have mapped the cosmic microwave background across the entire sky with remarkable precision, revealing subtle patterns that contain a wealth of information about the universe's composition, age, and evolution. But these satellites revealed something else, something unexpected, and that's where our story of dark flow begins. Now, let's get to the heart of the mystery. When astronomers study the cosmic microwave background, they're not just looking at its temperature variations. They can also use it to measure something called peculiar velocities. What's a peculiar velocity? It sounds odd, I know, but the term simply means the velocity of an object relative to the general expansion of the universe. Remember our balloon analogy? If the dots on the balloon were just sitting still on the surface, they would move apart purely due to the balloon's inflation. But what if some of those dots were also crawling across the surface in specific directions? That crawling motion would be their peculiar velocity, their motion above and beyond the expansion itself. Galaxies and galaxy clusters have peculiar velocities. They're not just carried along by the expansion, they're also pulled by gravity toward massive structures nearby. The Milky Way, for instance, is moving toward the Virgo cluster, a large collection of galaxies about 50 million light-years away. This motion is entirely due to gravity. The cluster's mass is pulling us toward it. But here's how we can measure these peculiar velocities using the CMB. As a galaxy cluster moves through space, it moves relative to the cosmic microwave background radiation. If the cluster is moving toward us, the CMB photons coming from that direction get slightly blue-shifted, compressed to higher energies, due to an effect called the kinematic Sunyaev-Zeldovich effect. If the cluster is moving away from us, the photons get redshifted. By measuring these subtle shifts in the CMB temperature in the direction of galaxy clusters, astronomers can determine how fast and in which direction these clusters are moving. This is precisely what a team of astronomers led by Alexander Kashlinsky set out to do in 2008. They examined the peculiar velocities of hundreds of galaxy clusters using WMAP data, expecting to find motions consistent with the gravitational pull of nearby large-scale structures. What they found instead was something that shouldn't exist according to our standard model of cosmology. The galaxy clusters weren't just moving randomly in different directions. They were flowing together, all streaming in roughly the same direction, toward a particular region of the sky in the constellation Centaurus. And they were moving fast at speeds of around 600 to 1,000 kilometers per second. To put that in perspective, that's about 2 million kilometers per hour. Imagine billions upon billions of stars, entire galaxy clusters, each containing the mass of thousands of galaxies, all flowing in concert like leaves carried by a cosmic current. Kashlinsky and his team called this phenomenon dark flow, and the name is fitting. The motion appears to be caused by something dark, something we can't see within our observable universe. So why did this discovery catch cosmologists off guard? Why is dark flow so problematic for our understanding of the universe? The issue comes down to scale and causality. According to the standard cosmological model, often called the lambda CDM model, the universe should be homogeneous and isotropic on large scales. That's a fancy way of saying it should look roughly the same in all directions, and its properties should be uniform when you average over sufficiently large volumes. The peculiar velocities we observe should be caused by gravitational attraction to matter within the observable universe. We see galaxies clustering together, forming filaments and sheets separated by vast voids. These structures create gravitational fields that pull on their surroundings. But here's the crucial point. The matter creating these gravitational fields should be visible in our surveys, either as normal matter we can see with telescopes or as dark matter we can detect through its gravitational effects. Dark flow suggests something different. The consistent motion of galaxy clusters across enormous distances, we're talking about regions spanning billions of light years, implies that they're being pulled by something outside the observable universe, or at least beyond the portion we can currently map. But wait, how can something outside the observable universe affect what's inside it? Doesn't that violate causality? This is where things get really interesting. The observable universe has a finite size, defined not by any edge in space, but by how far light has been able to travel since the Big Bang. The universe is approximately 13.8 billion years old, so we can only see objects whose light has had time to reach us. This creates a sphere around us, the observable universe, with a radius of about 46 billion light-years. Yes, that's larger than 13.8 billion light-years, because space itself has been expanding while light was travelling. Beyond this horizon, there's presumably more universe. But we can't see it, and according to our understanding of causality and the finite speed of light, it shouldn't be able to influence us. At least, not in ways we can currently detect. Yet dark flow suggests that there might be enormous structures beyond our cosmic horizon. Structures so massive that their gravitational influence extends into our observable bubble of the universe, pulling galaxy clusters in a coherent direction. Alternatively, and this is equally mind-bending, dark flow might indicate something fundamentally wrong with our cosmological models. Perhaps the universe isn't as uniform as we think. Maybe there are large-scale asymmetries in its structure or in its expansion that we haven't accounted for. Let's explore some of the ideas scientists have proposed to explain dark flow. Each one pushes the boundaries of our understanding in different ways. The external influence hypothesis. The first and perhaps most exciting explanation is that dark flow is real and is caused by matter outside our observable universe. This would mean there are enormous mass concentrations beyond our cosmic horizon, possibly gigantic structures that dwarf even the largest superclusters we can see. Some scientists have speculated about the existence of what they call mass concentrations, or even dark flow attractors, regions of space with such enormous mass that they can gravitationally influence galaxy clusters billions of light years away. But what could these be? One possibility involves the nature of the Big Bang and cosmic inflation. In the first fraction of a second after the Big Bang, the universe is thought to have undergone a period of exponential expansion called cosmic inflation. This inflation smoothed out most irregularities, but it also stretched the universe to sizes far larger than our observable portion. If the universe is vast enough, perhaps even infinite, then there could be structures at scales we can't observe directly. And these structures might have gravitational influences that reach into our cosmic neighborhood. Another, even more speculative idea relates to the multiverse. Some versions of cosmic inflation theory suggest that inflation didn't happen uniformly everywhere. Instead, different regions of space might have stopped inflating at different times, creating separate bubble universes, each potentially with different physical properties. Could dark flow be evidence of gravitational influence from another universe bubble? It's an extraordinary claim, and as Carl Sagan famously said, extraordinary claims require extraordinary evidence. The evidence for this interpretation remains controversial and far from conclusive. The cosmological principle violation. Another explanation is that dark flow might indicate a violation of the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. Perhaps our observable universe sits in a region that isn't typical, where there are large-scale gradients in density or in the rate of expansion. Imagine if the Big Bang didn't happen perfectly uniformly. If there were slight asymmetries in how the universe expanded or in how matter was distributed at the larger scales, we might see coherent flows of galaxy clusters. This would require rethinking some fundamental assumptions in cosmology, but it wouldn't necessarily break our understanding of physics. Some researchers have suggested that our observable universe might be part of a larger, inhomogeneous structure, perhaps a supervoid or a superhump in the cosmic density field. If we're situated in such a region, the gravitational effects could create the kind of bulk flow we observe as dark flow. Measurement error and systematic effects. Of course, there's another possibility that scientists must always consider. What if dark flow isn't real at all? What if it's an artifact of our measurements? A systematic error in how we're interpreting the data? This is not just skepticism for its own sake. The signals used to detect dark flow are incredibly subtle. The kinematic Sunyaev-Zeldovich effect involves temperature changes in the cosmic microwave background on the order of tens of microkelvins, millionths of a degree. Extracting such tiny signals from noisy data requires sophisticated statistical techniques. And there are many potential sources of error. For instance, there could be contamination from foreground sources, radio galaxies, dust in our own galaxy, or other astrophysical phenomena that create temperature fluctuations in the microwave sky. There could be biases in how galaxy clusters are selected for study, or errors in estimating their distances and masses. Several research teams have attempted to verify or refute the dark flow claim, and the results have been mixed. Some studies have found evidence supporting the existence of dark flow, while others have found no significant signal, or have argued that the apparent flow can be explained by known structures within the observable universe. Part 6. The Scientific Debate. The discovery of dark flow sparked intense debate in the cosmological community, and that debate continues today. Let's look at how science works when faced with such a puzzling observation. When Kashlinsky and his colleagues first announced their findings, they were careful to present them as intriguing but requiring further investigation. The initial analysis used data from WMAP and looked at several hundred galaxy clusters. The signal seemed robust, persisting even when they applied various statistical tests. But as other researchers began to examine the data and the methodology, questions emerged. Some teams analysed the same WMAP data, but used different approaches to account for systematic errors. In several cases, these alternative analyses found weaker evidence for dark flow or no evidence at all. Then came data from the Planck satellite, which observed the cosmic microwave background with even greater precision than WEAP. If dark flow were a real strong effect, Planck should have detected it even more clearly. Some analyses of Planck data did find hints of bulk flow, but the magnitude was smaller and less significant than what the original dark flow studies suggested. This is exactly how science should work. An unexpected result is published, other scientists attempt to replicate it using independent data or different methods, and gradually a consensus emerges about what's real and what might be an artifact. The process can be frustratingly slow, especially for those of us eager to know the answer, but it's the most reliable way we have to distinguish truth from error. As of now, the scientific community remains divided on dark flow. Some researchers maintain that there is evidence for coherent bulk flows of galaxy clusters that can't be easily explained by known structures. Others argue that improved analyses and better data have essentially ruled out the original dark flow claims, or at least reduce them to much smaller effects that might be consistent with our standard cosmological models. What's important to understand is that this uncertainty doesn't represent a failure of science, it represents science in action. We're dealing with incredibly difficult measurements at the edge of what our instruments can detect, and it's natural that different teams might reach different conclusions. Part 7. The broader context of cosmic flows. To fully appreciate the dark flow controversy, we need to understand it in the context of other large-scale motions in the universe. Galaxy clusters don't just sit still, they move, pulled by gravity toward concentrations of mass. Let's talk about some of the known structures that create cosmic flows. The Great Attractor. In the 1970s and 1980s, astronomers noticed that our local group of galaxies, which includes the Milky Way, Andromeda, and several dozen smaller galaxies, is moving at about 600 kilometers per second relative to the cosmic microwave background. This motion wasn't random. It seemed to be directed toward a specific region of the sky. Further investigation revealed the presence of what astronomers called the Great Attractor, a massive concentration of matter located about 150 to 250 million light-years away in the direction of the constellations Hydra and Centaurus. The Great Attractor is gravitationally pulling our local group, along with thousands of other galaxies, towards it. But here's the thing. When astronomers tried to observe the Great Attractor directly, they found it difficult to see. Part of the problem is that it lies in a direction obscured by the plane of our own Milky Way, where dust and stars block our view. But even accounting for this, the visible matter in that region didn't seem massive enough to explain the observed motion. Later observations revealed that the Great Attractor is part of an even larger structure called the Laniakea supercluster. This immense cosmic structure contains about 100,000 galaxies and has a total mass of about 100 million billion suns. Our galaxy, along with the Great Attractor and many other clusters, is part of this supercluster, all moving together through space. The Shapley concentration. But it doesn't end there. Beyond the Great Attractor, in roughly the same direction, lies an even more massive structure, the Shapley concentration, or Shapley supercluster. This is one of the most massive known structures in the observable universe, containing thousands of galaxies in a region about 650 million light-years away. The Shapley concentration is so massive that its gravitational pull influences motion on truly cosmic scales. Some of the motion of our local group, and indeed the flow of galaxies we observe, can be attributed to the gravitational attraction toward this enormous concentration of matter, the dipole in the cosmic microwave background. There's another piece of this puzzle worth mentioning. When we observe the cosmic microwave background, we see a dipole pattern. One side of the sky is slightly warmer, and the opposite side is slightly cooler. This pattern is exactly what you'd expect if we're moving through space relative to the rest frame of the CMB. Indeed, this dipole tells us that our solar system, along with the Milky Way and our local group, is moving at about 370 kilometers per second relative to the cosmic microwave background. This motion is partly due to the Earth orbiting the Sun orbiting the galaxy, the Milky Way moving within the local group, and the local group moving toward the Great Attractor and the Shapley concentration. So we know that cosmic flows exist. The question is whether dark flow represents something beyond these known motions, something that can't be explained by the structures we can see within the observable universe. Part 8. Technical challenges in measuring dark flow. Let's delve a bit deeper into why measuring dark flow is so technically challenging. Understanding these difficulties helps us appreciate both the boldness of the original claim and the reasons for ongoing skepticism. The kinematic Sunyaev-Zeldovich effect. Remember how I mentioned that we can detect the motion of galaxy clusters by observing how they affect the cosmic microwave background. This effect, called the kinematic Sunyaev-Zeldovich effect, or KSZ effect, is incredibly subtle. Here's how it works, in a bit more detail. As the cosmic microwave background photons travel through space toward us, some of them pass through galaxy clusters. These clusters contain hot gas with temperatures of millions of degrees. When CMB photons interact with the electrons in this hot gas, they can gain or lose energy through a process called inverse Compton scattering. If the cluster is stationary relative to the CMB, these interactions create what's called the thermal Sunyaev-Zeldovich effect. They shift the spectrum of the CMB in a predictable way. But if the cluster is moving, there's an additional effect, the kinematic Sunyaev-Zeldovich effect. The moving electrons impart a Doppler shift to the photons, creating a tiny temperature change in the CMB in the direction of that cluster. The magnitude of this temperature change depends on how fast the cluster is moving and how much hot gas it contains. For typical cluster velocities of hundreds of kilometers per second, the KS effect creates temperature changes of only about 10 to 100 microkelvins. To put that in perspective, the average temperature of the CMB is about 2.7 Kelvin, or 2,700,000 microkelvins. We're trying to measure variations that are less than 1 part in 10,000 of this already cold temperature. Noise and contamination. Detecting such a tiny signal requires exquisite sensitivity and careful data analysis. But the challenge doesn't stop there. The cosmic microwave background sky is full of other signals that can obscure or mimic the KSZ effect. There's the thermal Sunyaev-Zeldovich effect I mentioned, which is actually much stronger than the kinematic effect, but has a different spectral signature. There are point sources, radio galaxies, and dusty galaxies that emit microwave radiation. There's emission from dust in our own galaxy. There's the intrinsic temperature variation in the CMB from the early universe. All of these can contaminate our measurements. To extract the KSZ signal, astronomers must carefully model and subtract all these other sources of microwave emission. They must also accurately know the positions and properties of the galaxy clusters they're studying. Any errors in these steps can create false signals or mask real ones. Statistical challenges. Even if we can measure the KSZ effect for individual clusters, detecting a coherent bulk flow requires statistical analysis of many clusters. We need to look for a pattern. Do clusters across a large region of the sky all show motions in the same general direction? This is where things get tricky. The peculiar velocities of individual clusters have random components due to local gravitational interactions. To detect a bulk flow underlying these random motions, we need to average over many clusters and use sophisticated statistical techniques. Different research teams have used different statistical approaches, and these differences can lead to different conclusions. Some methods might be more sensitive to certain types of systematic errors. Others might make assumptions about the data that aren't fully justified. This technical complexity is one reason why the dark flow controversy has been so difficult to resolve. It's not simply a matter of pointing a telescope and seeing something clearly. It's a matter of extracting the faintest of signals from noisy data, requiring multiple layers of complex analysis where each step introduces potential errors or biases. Part 9. Alternative Theories and Cosmic Models. The dark flow mystery has prompted some scientists to consider whether our fundamental understanding of cosmology might need revision. Let's explore some of these alternative ideas. Inhomogeneous cosmology. Our standard model of cosmology, the lambda CDM model, assumes that the universe is homogeneous and isotropic, that it looks basically the same in all directions when averaged over large enough scales. But what if this assumption is wrong, at least partially? Some researchers have proposed inhomogeneous cosmological models where the universe has large-scale variations in density or expansion rate. In these models, we might be located in a region that's not typical of the universe as a whole. For instance, imagine if our observable universe sits in a region that's slightly less dense than average, surrounded by denser regions. This could create pressure differences that drive bulk flows of matter, or perhaps the expansion rate isn't perfectly uniform. Maybe some regions are expanding faster than others, creating large-scale peculiar velocities. These models can potentially explain dark flow without requiring mysterious influences from beyond the observable universe. However, they face their own challenges. The cosmic microwave background observations suggest that the universe was remarkably uniform in the early stages, creating large-scale inhomogeneities that persist to the present day requires special conditions in the early universe, and not all of these conditions are well motivated by fundamental physics. Modified gravity theories. Another avenue of exploration involves modifying our theory of gravity itself. Einstein's general relativity has been extraordinarily successful in explaining gravitational phenomena, but it's possible that it needs modification on the largest cosmic scales. Some modified gravity theories, such as MOND, modified Newtonian dynamics, and its relativistic extensions, were originally proposed to explain galaxy rotation curves without invoking dark matter. Could similar modifications to gravity also explain large-scale flows like dark flow? The challenge here is that any modified gravity theory must still match all the other observations that general relativity explains so well. From the orbits of planets to the bending of light around massive objects to the behavior of black holes. Finding a theory that does all of this while also explaining dark flow is a tall order. Cosmological anomalies and the axis of evil. Dark flow isn't the only cosmological puzzle that has astronomers scratching their heads. When analysing the cosmic microwave background, researchers have found several unexpected patterns that don't fit neatly with the standard model. One of these is sometimes called the axis of evil, a rather dramatic name for an intriguing alignment. The larger scale temperature fluctuations in the CMB seem to have a preferred orientation, aligned along a particular axis through the universe. This is surprising because the CMB should be isotropic, having no preferred directions. There's also the cold spot, an unusually large cold region in the CMB that's difficult to explain with standard cosmological models. Some scientists have wondered whether it might be associated with a supervoid, an enormous underdense region, though this explanation has its own problems. These anomalies might be unrelated to dark flow, or they might be pieces of the same puzzle, hints that something about our cosmological models needs adjustment. The challenge is figuring out what's a real signal demanding explanation, and what's just a statistical fluke that we shouldn't read too much into. When you analyse data with as many possible patterns as the CMB has, you're bound to find some apparent anomalies just by chance. The question is, which ones are meaningful? Part 10. The latest observational campaigns. The debate over dark flow has motivated new observational campaigns designed to either confirm or refute its existence. Let's look at some of the ways astronomers are currently tackling this mystery. Improved CMB experiments. The Planck satellite, which operated from 2009 to 2013, provided the most detailed map of the cosmic microwave background to date. Its data has been used by multiple research teams to search for signs of bulk flow. Some analyses of Planck data have found evidence for coherent motions of galaxy clusters, though generally at lower amplitudes than the original dark flow claim suggested. Other analyses have found results consistent with our standard cosmological models, with no need to invoke unusual bulk flows. The next generation of CMB experiments is already under development. These include ground-based telescopes like the Simons Observatory and the CMB-S4 project, as well as proposed space missions. These experiments will have even greater sensitivity and resolution, potentially settling the dark flow question once and for all. Large-scale structure surveys. Another approach is to map the three-dimensional distribution of galaxies across larger volumes of the universe. Surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time are creating detailed maps of cosmic structure. By understanding the distribution of matter in the universe more completely, astronomers can better predict what peculiar velocities we should see. If observed flows match these predictions, it suggests our models are on the right track. If they don't, it might support the idea that there are influences we're not accounting for, possibly including dark flow. Peculiar velocity surveys. Some researchers are taking a more direct approach by measuring the peculiar velocities of galaxies using techniques that don't rely on the KS-Seed effect. One method involves comparing two independent distance measurements: the redshift distance, based on the expansion of the universe, and the luminosity distance, based on how bright a galaxy appears. The difference between these two distances reveals the galaxy's peculiar velocity, its motion relative to the cosmic expansion. This technique has been used to map flows around the Great Attractor and to study the influence of the Shapley concentration. These direct velocity measurements can potentially confirm or contradict the KS-Seed-based claims about dark flow. If multiple independent methods converge on the same answer, our confidence in the result increases substantially. Part 11. Implications for cosmology. Let's step back and consider what dark flow, if it's real, would mean for our understanding of the universe. The edge of the observable universe. One of the most profound implications would be evidence for influences beyond our cosmic horizon. Throughout history, humans have continually discovered that the universe is larger than we imagined. We went from thinking Earth was the center of everything to understanding it as a planet orbiting an ordinary star in an ordinary galaxy, which is itself part of a vast cosmic web containing hundreds of billions of galaxies. Dark flow might be telling us that even our observable universe, already incomprehensibly vast, is just a small part of a much larger structure. There could be enormous mass concentrations beyond what we can see, influencing the motion of matter within our cosmic neighborhood. This would be both humbling and exciting. Humbling because it would remind us how tiny our observable bubble is compared to the full extent of reality. Exciting because it would give us an indirect way to learn about the universe beyond what we can directly observe. The nature of cosmic inflation. Dark flow might also tell us something about cosmic inflation, that brief period of exponential expansion in the universe's first moments. Different models of inflation make different predictions about the size and structure of the universe on scales larger than what we can observe. Some models suggest that inflation created a universe that's only slightly larger than what we can see, perhaps 10 or 100 times bigger. Other models suggest the universe might be vastly larger, perhaps infinite, with structures at scales we can barely imagine. If dark flow is caused by structures beyond our horizon, it might help us distinguish between these different inflationary scenarios. The cosmological principle. Remember the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. This principle isn't just a philosophical preference, it's a cornerstone of modern cosmology. It allows us to use Einstein's equations to model the evolution of the entire universe based on observations of our local part of it. If dark flow indicates large-scale asymmetries or flows that violate this principle, we might need to rethink some of our basic assumptions. This doesn't mean all of cosmology is wrong. Our models work extremely well for describing most observations, but it might mean we need more sophisticated models that account for variations on the largest scales. Dark energy and the expansion of the universe. There's also a possible connection to one of cosmology's other great mysteries, dark energy, the unknown force that's causing the expansion of the universe to accelerate. Dark energy makes up about 68% of the total energy content of the universe, yet we have no idea what it is. Could dark flow somehow be related to dark energy? Some speculative theories suggest that dark energy might not be perfectly uniform throughout space. If there are variations in dark energy density or pressure, these could potentially create large-scale flows. This is highly speculative, and most physicists don't see a clear connection, but the possibility reminds us how much we still don't understand about the universe's fundamental composition. Part 12. The current state of the debate. Where do things stand now? What's the current scientific consensus, if there is one, on dark flow? The honest answer is that the question remains open. The original claims of dark flow from the late 2000s have been substantially challenged, and many cosmologists are skeptical that the effect is as large or as significant as initially suggested. Improved analyses of CMB data, particularly from the Planck satellite, have generally found weaker evidence for bulk flows, and some studies have found no significant evidence at all. However, the issue hasn't been completely resolved. Some research groups continue to find hints of coherent, large-scale flows in their analyses, though often with different characteristics than the original dark flow claims. These flows might be smaller in amplitude, or they might be directed toward different regions of the sky, or they might only appear in certain subsets of the data. Part of the challenge is that we're dealing with measurements at the very edge of detectability, where systematic errors and statistical uncertainties are significant. Different research teams make different choices about how to analyze the data, which clusters to include how to model contaminating signals and which statistical tests to apply. These choices can affect the conclusions. It's also worth noting that even if the specific claims about dark flow turn out to be incorrect, the research has value. The attempt to measure bulk flows has pushed forward our techniques for analyzing CMB data and studying galaxy cluster properties. It's prompted new observations and new theoretical work. Even negative results, definitively ruling out certain effects, advance our understanding. Science often progresses this way. A provocative claim motivates intensive scrutiny, new observations, and theoretical exploration. Sometimes the original claim is vindicated, sometimes it's refuted. Often the truth is more nuanced than either extreme. Regardless, the process advances our knowledge. Part 13. What comes next? So what does the future hold for dark flow research? What observations or discoveries might finally settle the question? Next generation telescopes and surveys. The coming decade will see a revolution in astronomical observing capabilities. The Vera C. Rubin Observatory, beginning operations soon, will survey the entire visible sky every few nights, creating an unprecedented movie of the universe. Its deep, wide-area observations will help us map cosmic structure in 3 dimensions with far greater completeness than ever before. The Square Kilometre Array, a next-generation radio telescope being built in Australia and South Africa, will allow us to map the distribution of neutral hydrogen gas across huge volumes of the universe. This will give us another way to trace the cosmic web and measure large-scale flows. Future space missions focused on the cosmic microwave background, if approved, could provide even more sensitive measurements of the kinematic Sunyaev-Zeldovich effect, potentially detecting bulk flows that current experiments can't quite pin down. Better theoretical models. On the theoretical side, cosmologists are working on more sophisticated simulations of the universe's evolution. Modern simulations can follow the growth of structure from tiny fluctuations in the early universe to the complex cosmic web we see today, including the formation of individual galaxies. By running these simulations with different assumptions and comparing them to observations, researchers can test whether dark flow, or any other observed large-scale motion, can be explained within our standard cosmological framework, or whether it requires new physics. These simulations are also helping us understand the observational biases and systematic errors that affect measurements of bulk flows. By creating mock observations from simulated universes where we know the true answer, we can test whether our analysis techniques would correctly recover that answer from noisy, realistic data. Multi-messenger astronomy. An exciting new development is the use of gravitational waves to study cosmology. The detection of gravitational waves from merging black holes and neutron stars has opened an entirely new window on the universe. In the future, gravitational wave observatories might be able to measure the expansion of the universe independently of electromagnetic observations. They could potentially detect peculiar velocities of galaxies and galaxy clusters through the precise localization of gravitational wave sources and their host galaxies. This would give us a completely independent check on measurements of cosmic flows, including any potential dark flow signature. Similarly, neutrino astronomy is advancing. High-energy neutrinos from cosmic sources might eventually provide yet another way to map the universe's structure and study its large-scale dynamics. The power of multi-messenger astronomy is that it allows us to cross-check our findings using completely different types of observations. If multiple independent methods all point to the same conclusion about dark flow, either confirming or refuting it, we can be much more confident in the answer. Part 14. The bigger picture, what we know and don't know. Taking a step back, the dark flow controversy fits into a much larger story about the current state of cosmology. We live in an extraordinary time. In just the past few decades, we've gone from having rough estimates of the universe's age and composition to having precise measurements that allow us to trace cosmic history with remarkable confidence. We know the universe is 13.8 billion years old, give or take a few 100 million years. We know it began in a hot, dense state, the Big Bang, and has been expanding ever since. We know that about 5% of the universe is made of ordinary matter, the atoms that make up stars, planets, and people. About 27% is dark matter, a mysterious substance that we detect only through its gravitational effects. And about 68% is dark energy, an even more mysterious component that's causing the expansion of the universe to accelerate. These are extraordinary achievements. The fact that we can make such precise statements about the universe's composition and history is a testament to human ingenuity and the power of the scientific method. But for all that we know, there's still so much we don't understand. What is dark matter made of? Decades of searching haven't yet identified the particle or particles responsible. What is dark energy? We've given it a name, but we have almost no idea what it actually is, whether it's a property of space itself, a new field permeating the universe, or something else entirely. And then there are questions like dark flow. Even if we can precisely measure how the universe is moving, do we fully understand why? Are there influences we haven't accounted for, structures beyond what we can see, or are we simply dealing with the statistical messiness of a universe that's complex on every scale? These gaps in our knowledge aren't failures, they're frontiers. They're the areas where the next generation of discoveries will be made, and that's exciting. Part 15. Philosophical implications. Let's take a moment to consider some of the deeper philosophical questions that dark flow raises. What can we know about the universe? The existence of an observable universe, a finite region of space beyond which we cannot see, raises profound questions about the limits of knowledge. If dark flow is real and is caused by something beyond our cosmic horizon, it would be an example of learning about the unobservable through its effects on what we can observe. This isn't entirely new. Scientists regularly make inferences about things they can't directly detect. We've never seen a quark in isolation, but we know they exist because of their effects in particle colliders. We can't see dark matter directly, but we infer its presence from gravitational effects on visible matter. But there's something particularly striking about influences from beyond the observable universe. These aren't just things that are hard to see. They're things that are, in principle, impossible to observe with light, because that light hasn't had time to reach us since the Big Bang. Yet gravity, operating at the speed of light but starting earlier, might extend its influence across these boundaries. This raises a fascinating question. How much can we learn about regions of space that are fundamentally beyond our observational horizon? If dark flow is real, it suggests that the answer is more than you might think. The observable universe isn't an isolated system. It's influenced by what lies beyond it, and by studying these influences carefully, we might be able to piece together clues about that larger reality. The scale of reality. Human intuition evolved to deal with objects on human scales, things we can see, touch, and interact with directly. We're reasonably good at understanding how medium-sized objects behave, how water flows, how stones fall, how fire burns, but the universe challenges our intuition at every turn. At the quantum scale, particles behave in ways that seem bizarre, existing in multiple states simultaneously, appearing to influence each other instantaneously across vast distances. At the cosmic scale, space itself expands, carrying galaxies along with it, and time flows at different rates depending on how fast you're moving or how deep you are in a gravitational field. Dark flow, if it's real, represents yet another challenge to human intuition. The idea that structures spanning billions of light years are all flowing in the same direction, pulled by something we can't even see, is almost impossible to visualize. How do you picture a galaxy cluster with the mass of thousands of galaxies, each containing hundreds of billions of stars, each containing billions upon billions of atoms, all moving together as a coherent flow? The scales involved are so vast that they defeat our attempts at intuitive understanding. We can work with the mathematics, we can make measurements, we can create computer simulations, but we can't really hold the full reality in our minds all at once. And yet somehow, we can still study it. We can make predictions, test hypotheses, and gradually build up a picture of how the universe works. That's both humbling and empowering. Our place in the cosmos. Throughout history, major scientific discoveries have consistently revealed that humans are less central to the cosmic story than we once thought. Earth isn't at the centre of the solar system. The solar system isn't at the centre of the galaxy. Our galaxy isn't at the centre of the universe. In fact, there is no centre of the universe in any meaningful sense. Each of these discoveries required us to revise our understanding of our place in the cosmos. The Copernican revolution wasn't just about planetary orbits. It was about recognizing that we don't occupy a special position. Dark flow, in a way, continues this trend. If it's real, it suggests that even our observable universe, this bubble of space containing hundreds of billions of galaxies, is just a small part of something much larger. The structures that matter, that shape the flow of galaxies, extend beyond what we can ever hope to see directly. This might seem depressing, another reminder of cosmic insignificance, but I think there's another way to look at it. The fact that we, Small creatures on a small planet can even ask these questions and make progress toward answering them is remarkable. The universe doesn't owe us the ability to understand it, yet through careful observation and reasoning, we've managed to figure out an enormous amount. Whether or not dark flow is real, the fact that we can detect motions of galaxy clusters billions of light years away by measuring minute temperature variations in the cosmic microwave background is an extraordinary achievement. It's worth celebrating what we've learned, even as we acknowledge how much remains unknown. Part 16. Lessons from the dark flow debate. The ongoing controversy over dark flow offers some valuable lessons about how science works, not just in theory, but in practice. The importance of skepticism. Science is often portrayed as a process of making discoveries, finding new things, answering questions, expanding the frontier of knowledge. And it is all of those things. But science is also a process of rigorous skepticism, of questioning claims, of demanding evidence, of trying to find flaws in arguments and errors in data. When the initial dark flow results were published, the scientific community didn't simply accept them at face value. Other researchers immediately began scrutinizing the analysis, checking for potential errors, looking for alternative explanations. This skepticism isn't personal or hostile, it's how science ensures that its conclusions are reliable. The default position in science isn't to accept new claims, but to test them rigorously. Extraordinary claims require extraordinary evidence, as the saying goes. Dark flow is certainly an extraordinary claim. It suggests either massive structures beyond the observable universe or a breakdown in our cosmological models. Such a claim demands thorough investigation. The challenge of being wrong. One of the hardest things in science is admitting that you might be wrong. Scientists are human, and humans naturally become attached to their ideas. When you've invested years of work into a particular hypothesis, when you've published papers and given talks about it, it can be psychologically difficult to let go if evidence turns against you. But good science requires exactly this willingness to follow the evidence wherever it leads, even if it means abandoning cherished ideas. The history of science is full of theories that were once widely accepted, but were eventually discarded when better evidence came along. We don't yet know whether dark flow will join that list, but however the controversy resolves, it will be a testament to the self-correcting nature of science. If dark flow is real, the initial skepticism will have helped ensure that we have solid evidence before accepting such an extraordinary claim. If it's not real, the scientific process will have caught the error before it became entrenched in our understanding of the cosmos. The provisional nature of scientific knowledge. It's important to understand that scientific knowledge is always provisional. When we say we know something scientifically, we mean that we have strong evidence supporting it and no compelling evidence against it, not that we're absolutely certain it will never be revised. This can be uncomfortable. People often want definitive answers, certainty, closure. But the universe is complex, and our understanding of it is always incomplete. The best we can do is follow the evidence, update our beliefs when new data arrives, and hold our conclusions with appropriate confidence based on the strength of the evidence. Right now, we can't say with certainty whether dark flow is real. We can only say what the current evidence suggests, acknowledging the uncertainties and limitations of our measurements. That might not be satisfying, but it's honest, and honesty is fundamental to the scientific enterprise. Part 17. The human element in cosmology. Behind all these technical discussions of galaxy clusters and cosmic microwave background measurements are people, astronomers, physicists, graduate students, postdocs, professors, all trying to make sense of the universe. Let's take a moment to appreciate the human side of this story. The excitement of discovery. Imagine being on the research team that first noticed the dark flow signal. You're analysing data from WMAP, looking at the peculiar velocities of galaxy clusters, expecting to see random motions, perhaps some flows toward known structures. But instead, you see a pattern, clusters across a huge region of the sky, all moving in roughly the same direction. Your first thought is probably that you've made a mistake. Maybe there's a bug in your code, or you've misidentified some of the clusters, or there's a systematic error you haven't accounted for. So you check everything again and again. You apply different statistical tests. You look at different subsets of the data. But the signal persists. Gradually, the realization dawns. This might be real. You might have discovered something fundamentally new about the universe. Your pulse quickens. This is what you became a scientist for. Moments like this, when years of study and work are suddenly pay off, with a glimpse of something no one has ever seen before. But then comes the hard part, convincing the rest of the scientific community. You have to write papers that explain your findings clearly, that address potential objections, that demonstrate you've been careful and rigorous. You give talks at conferences, where colleagues pepper you with questions, some supportive, some skeptical, all probing for weaknesses in your arguments. This is the life of a scientist working at the frontier of knowledge. It's exciting, but it's also challenging and sometimes frustrating. The burden of uncertainty. On the other side are the skeptics, researchers who look at the same data and reach different conclusions, or who find reasons to doubt the original claims. They're not trying to be difficult or obstruct progress. They're fulfilling an essential role in the scientific process. They're the quality control, the devil's advocates, the ones who ensure that only robust, well-supported conclusions make it into our scientific understanding. But this role comes with its own challenges. It's easy to be perceived as negative, as someone who's just tearing down others' work without contributing anything positive. In reality, rigorous critical evaluation is one of the most positive contributions you can make to science. It's how we separate truth from error. And for everyone involved, there's the burden of uncertainty. When you're working at the cutting edge, you rarely have the luxury of clear, unambiguous answers. Data is noisy, analysis methods have limitations. Alternative explanations can rarely be completely ruled out. You have to make judgments about what the evidence supports, knowing that you might be wrong. This requires a particular kind of intellectual humility, the ability to hold your conclusions tentatively, to update your beliefs when new evidence arrives, to say, I don't know, when you genuinely don't. These aren't easy things for anyone, but they're essential for good science. The long arc of scientific progress. It's worth remembering that most scientific questions aren't answered quickly. The dark flow controversy has been ongoing for over 15 years now, and we still don't have a definitive resolution. For the researchers involved, this represents a significant fraction of their careers. This is normal in science, especially in fields like cosmology, where observations are difficult and interpretations are complex. The question of whether the universe is expanding wasn't settled by a single observation. It took decades of work by many researchers. The nature of dark matter has been debated for nearly a century and remains unresolved. Scientific progress often feels slow from the inside. But when you zoom out and look at the bigger picture, the achievements are remarkable. In just a few generations, we've gone from not knowing whether other galaxies exist to mapping the large-scale structure of the observable universe. We've gone from rough guesses about the universe's age to precise measurements. We've discovered that most of the universe is made of components we don't fully understand: dark matter and dark energy. Each of these advances built on thousands of individual contributions, observations, calculations, theoretical insights, experimental tests. Progress is cumulative, with each generation of scientists building on the work of those who came before. Whether or not dark flow turns out to be real, the research will have contributed to this grand project. We'll have better techniques for analysing CMB data, better understanding of galaxy cluster properties, better theoretical models of cosmic flows, and that's how science advances, not always with dramatic breakthroughs, but often with incremental improvements in our understanding, each one opening up new questions to explore. Part 18. Looking to the future. As we near the end of our journey through the dark flow mystery, let's look ahead to what the future might hold, both for this specific question and for cosmology more broadly. Settled science or enduring mystery? Will we ever definitively know whether dark flow is real? The answer depends partly on the nature of the phenomenon itself. If dark flow is a strong effect caused by massive structures just beyond our current observational horizon, then improving our measurements should eventually settle the question. As we map more of the universe in greater detail, as we measure the cosmic microwave background with ever greater precision, the evidence should become clearer one way or another. But if dark flow is a subtle effect, just barely at the edge of detectability, or if it varies in complex ways across the sky, the question might remain contentious for a long time. Sometimes in science, questions don't get answered with a dramatic eureka moment, but rather fade away as they become less interesting compared to new puzzles that emerge. It's also possible that the answer will be nuanced. Perhaps there are bulk flows larger than our standard models predict, but smaller than the original dark flow claim suggested. Perhaps the flows have different characteristics than initially thought. Science often progresses not by proving ideas completely right or completely wrong, but by refining our understanding, adding nuance and detail to our picture of reality. The next generation of cosmologists. Right now, there are students around the world, perhaps some of you reading this, who will become the next generation of cosmologists. They'll be the ones who benefit from the new telescopes and experiments currently under development. They'll be the ones who analyse the data, develop new theoretical models, and push our understanding forward. What will they discover? It's impossible to predict with certainty, but history suggests that the universe still has plenty of surprises in store for us. Every time we've developed new ways of observing the cosmos, from optical telescopes to radio telescopes, to space-based observatories, to gravitational wave detectors, we've discovered things we didn't anticipate. The cosmic microwave background itself was discovered by accident. Dark energy was a complete surprise when observations in the late 1990s showed that the universe's expansion is accelerating. Gravitational waves, while predicted by Einstein's theory, weren't detected until 2015, 100 years after the theory was published, and they've already revealed a population of black holes we didn't know existed. What will be the next surprise? Perhaps dark flow will turn out to be more significant and more bizarre than even its proponents initially thought. Perhaps we'll discover other large-scale phenomena that challenge our cosmological models in new ways. Perhaps we'll finally figure out what dark matter and dark energy are. Or perhaps we'll encounter something entirely unexpected, a phenomenon we don't even have a name for yet. The practical value of cosmology. You might wonder, why does any of this matter? Galaxy clusters flowing through space billions of light years away. What difference does it make to life here on Earth? It's a fair question. Cosmology doesn't have the obvious practical applications of, say, materials science or medicine. You can't build a better smartphone or cure a disease by understanding dark flow, but basic research into the fundamental nature of reality has a track record of eventually leading to practical applications, often in ways that couldn't have been predicted. Quantum mechanics was once purely theoretical physics, of no apparent practical use. Today, it's the foundation of modern electronics, from computer chips to MRI machines to solar panels. General relativity. Einstein's theory of gravity that underlies modern cosmology seemed like pure abstraction when it was developed. Today, It's essential for GPS satellites to work properly. Without accounting for relativistic effects, GPS would accumulate errors of several kilometers per day. We can't know what practical applications might eventually emerge from our understanding of cosmology. But beyond practical benefits, there's another reason to care about these questions. They're part of humanity's eternal quest to understand our place in the universe. Who are we? Where did we come from? What is this vast cosmos we find ourselves in? These are questions humans have asked for as long as we've been able to ask questions. Science has given us ways to actually answer them. Not with myths or speculation, but with evidence and rigorous reasoning. That's valuable in itself. Understanding the universe enriches our lives, expands our perspective, and connects us to something larger than our individual concerns. It reminds us that we're part of a story that began 13.8 billion years ago and will continue for billions or trillions of years into the future. Part 19. Final Thoughts on Cosmic Mystery. As we come to the close of our exploration, it's worth reflecting on what the dark flow mystery tells us about the nature of scientific inquiry and our relationship with the unknown. The beauty of unsolved problems. There's something deeply appealing about unsolved mysteries in science. They represent the frontier, the places where our knowledge gives way to the unknown. They're invitations to explore, to think creatively, to push the boundaries of what's possible. Solved problems are satisfying. There's real pleasure in understanding something fully, in having questions answered. But unsolved problems are exciting. They're where the action is, where discoveries wait to be made. Dark flow, whether it ultimately proves real or not, has served this purpose beautifully. It's prompted new observations, inspired theoretical work, challenged assumptions, and reminded us that the universe still has secrets. Even if the phenomenon turns out to be an artifact of our measurements or a subtle effect that fits within our existing models, the journey of investigating it has been worthwhile. And if it does turn out to be real, if there really are massive structures beyond the observable universe pulling on our galaxy clusters, or if there's something fundamentally wrong with our cosmological models, then we're in for an even more exciting ride. A confirmed dark flow would open up new questions. What are these structures? How did they form? What else might they tell us about the universe beyond what we can see? Living with uncertainty. One of the most important skills in science, and perhaps in life more broadly, is learning to be comfortable with uncertainty. We want clear answers, definitive conclusions, absolute certainty. But reality rarely provides these, at least not immediately. The dark flow controversy exemplifies this. More than 15 years after the initial discovery was announced, we still don't have a definitive answer. The evidence is complex, the analyses are difficult, and different researchers reach different conclusions. This can be frustrating, but it's also honest. The universe doesn't care about our desire for simple answers. It is what it is, and all we can do is observe it as carefully as possible, analyze our observations as rigorously as possible, and draw conclusions that are appropriately cautious given the limitations of our data. Science teaches us to proportion our confidence to the strength of the evidence. When the evidence is clear and strong, we can be confident. When it's ambiguous or limited, we should be tentative. This kind of epistemic humility, knowing what we know and what we don't know, is valuable beyond just science. It's a way of approaching the world that can help us navigate all kinds of uncertainties. The ongoing story. The story of dark flow isn't over. Somewhere right now, astronomers are analysing new data, refining their techniques, testing new hypotheses. Graduate students are working on their dissertations, perhaps using fresh approaches that will shed new light on the question. Engineers are building the next generation of telescopes and satellites that will push our observational capabilities forward. In a few years, we might have a clearer answer, or we might not. The question might evolve into something more nuanced, or it might be superseded by new mysteries that capture the field's attention. But whatever happens, the fundamental work of cosmology will continue. Humans will keep looking up at the night sky, asking questions about what's out there. We'll keep building better instruments, developing better theories, pushing our understanding further. Because ultimately, that's what we do. We're curious creatures, driven to explore and understand. The universe is vast and complex and often baffling, but it's also knowable, at least in part. Through patient observation and careful reasoning, we can figure things out. We can map the cosmos, trace its history, understand its fundamental properties. We might never know everything. The universe might always retain some mysteries, some aspects that lie forever beyond our ability to observe or comprehend. But we can keep trying, keep learning, keep pushing the boundaries of knowledge outward. And that in the end is what the mystery of dark flow represents. It's not just a question about galaxy clusters and cosmic microwave background measurements. It's part of humanity's larger project of making sense of the universe, a project that has occupied us for thousands of years and will continue for as long as humans exist. Conclusion. So where does this leave us with dark flow? Here's what we can say with confidence. Galaxy clusters move. They have peculiar velocities on top of the cosmic expansion, driven by gravitational attraction to massive structures. We can measure these velocities using various techniques, including the kinematic Sunyaev-Zeldovich effect on the cosmic microwave background. Some analyses of this data have suggested the presence of large-scale bulk flows, streams of galaxy clusters moving in coherent patterns across huge volumes of space. If real and as large as initially claimed, this would be challenging to explain with our standard cosmological models. It might indicate structures beyond the observable universe, or it might suggest that the universe is less uniform than we thought. However, other analyses have found weaker evidence for such flows, or no significant evidence at all. The measurements are difficult, the data analysis is complex, and there are many potential sources of systematic error. The scientific community remains divided on whether dark flow represents a real phenomenon requiring new physics or whether it's an artifact of our measurements and analysis techniques. Future observations from next-generation telescopes and satellites should help resolve the question. Better data and more sophisticated analysis methods will either confirm the existence of anomalous large-scale flows or rule them out definitively. In the meantime, the dark flow controversy reminds us of several important truths. The universe is vast and complex, operating on scales that challenge our intuition. Our understanding of it, while impressive, remains incomplete. Science is a process of constant questioning, testing, and refinement. And even when we can't yet answer a question definitively, the attempt to answer it drives progress. Whether you look up at the night sky and see just stars, or whether you see galaxy clusters streaming through space, pulled by mysterious forces toward unknown destinations, remember this: you're part of a universe that's stranger and more wonderful than we ever imagined. And every generation gets to add a little more to our understanding of it. The mystery of dark flow might one day be solved, but there will always be new mysteries waiting beyond it. New questions to ask, new frontiers to explore, and that's something to be excited about. Thank you for joining me on this journey through one of cosmology's most intriguing puzzles. Keep looking up, keep asking questions, and keep wondering about the universe we call home.